Hello students, hope you have studied electric field. Now let's discuss a bit more about electric field. Anywhere if you are asked to calculate electric field, what you will be doing? You will be simply placing a unit positive charge and you will calculate the force. The force experienced by unit positive charge will be the electric field, and the direction in which the unit positive charge is experiencing the field, that will be the direction of electric field also. So field is having a magnitude, field is having a direction. So if the field is uniform, then both magnitude and direction will be same everywhere. But if the field is non-uniform, then any one of this, that is magnitude, direction, or both, will be changing. So you have learned how to derive the expression of electric field, calculate the electric field due to point charges. Now let's see how we calculate electric field due to extended body. Whenever the charges are distributed in an extended body, then you take a element on that charge body whose charge you can assume as a point charge of dq, and the point where you are asked to calculate electric field, suppose that distance is r. So that elemental charge will give you an elemental field, that is k dq by r square. Now here over the whole body you will integrate to get your electric field over that whole substance, that is integration of k dq by r square. Here r and dq both are variable, so you substitute properly and then you integrate. Here the charge may be distributed linearly, surface, and even in volume. If the charge is distributed linearly, then we take linear charge density denoted by the symbol lambda. This is actually charge per unit length, Q by L. For elemental length, we write this lambda as dq by dl. So this charge dq is taken as lambda dl, where lambda is constant because charge is uniformly distributed. So you replace this dq by lambda dl and then integrate properly. If the charge is distributed over the surface, then we will have surface charge density denoted by the symbol sigma. This is charge present over the surface area. And here in calculus we are writing this sigma as dq by dA. So here we replace this dq as sigma dA, where sigma is constant, and then again you integrate properly. If the surface is distributed in a volume, then we are having volume charge density, which is denoted by rho. This is your charge per unit volume. And here we are writing in calculus, that is dq by dv, where dq is rho dv. So this way you can replace your dq by lambda dl, sigma dA, या rho dv, and then properly integrate. Suppose we have taken a charged ring. The charge is uniformly distributed over the ring, and consider this ring is of radius a. You are asked to calculate electric field along its axis, that is at a distance x from its center. As this ring is not a point charge, so you can't apply the formula k q by x square. Here you'll have to take this help. So take a very small element here. This elemental charge, which is suppose dq. Now this dq, assume that it is just stored at one point. You join this with point P and extend it. The direction of this field will be in this if the charge ring is positive. Similarly, you take just diametrically opposite another element of same length. Suppose that is also having a charge dq. So this point also you join with P and extend it, and the direction of this field will be this. Here your dE will be k dq by r square if this distance r, where your R is given by the formula root of a square plus x square. Now here, for every element, there are diametrically opposite element. So you can't simply integrate this because these are in different directions. Integration means, remember, algebraical summation. So you'll have to resolve these electric fields along x and y axis. Suppose these angles are theta. So vertically opposite this angle and this angle theta. So if you resolve the upward field, that is dE, so this component will be dE cos theta and this component will be dE sin theta. Similarly, this component if you resolve, then again your horizontal field is dE cos theta and vertical downward component is dE sin theta. So for every element, when you are taking your diametrically opposite element, you see for every cases this dE sin theta equal and opposite and cancels. So net vertical field, which is summation of dE sin theta, will be 0. But horizontal components are in same direction, so that to be added. So resultant field will be actually the summation of dE cos theta. As elements are large in number, so summation means here you will have to integrate this dE cos theta. Here dE is your k dq by r square, and you replace this cos theta in any one of this triangle. Cos theta will be your x by r. That means this will be k dq x by r cube. So here you see k, your x is also constant, r is also constant, only your dq here variable. So integration of dq will be q. So you integrate over the whole ring. Here as the charge is distributed over length, you can replace this dq also by lambda dl. So if you want to replace, then you will get k lambda x by r cube and integration of dl. So k lambda x by r cube, whereas integration of dl is L, and here L will be the whole ring, that is circumference, which is 2 pi a. So here it is k x r cube and this is lambda into L. So lambda into L will be the total charge present in the ring, that is k q x by r cube. So you see the electric field which you are getting, that electric field E is your k q x and r q means a square plus x square whole 3 by 2. This is actually your electric field due to a charged ring on its axis. You see your point charge formula is not valid, that is Coulomb's law is not valid. If you are asked to calculate the electric field in the center of this ring, then what we'll be doing? You'll be placing this x equal to 0. So at center x is equal to 0, you see E will be equal to 0. If your x is extremely greater than A, then you see this electric field will be kq by x square, where you just place this a as 0. So a square will be 0. This is your x cube. So we are getting kq by x square, and you see this is valid for your point charge kq by r square. So when your distance is very large, then you can think of that whole ring is a point where the charge is present in its center, and this is kq by x square. Another question you may get, that at what distance this electric field will be maximum. In that cases, you differentiate the electric field with respect to your distance and put it equal to 0. You solve, you will get your value of x where the field will be maximum. You practice this type of problems. Thank you.